In this session, I will be talking about creating different kinds of graphs in R. More and more of introduction to data visualization using R. So all the basic kinds of graphs are typically discussed in this session. So as a part of the agenda, we will be looking at what are the different types of graphs that we can look at. So if at all I have two variables, what are the different kinds of plots I can do? Wherein I would be talking about one of the most important plots, the scatter plot. Now once I have done a scatter plot, how do I add different kinds of shapes to the plot? Right, coming out with different kinds of points, coming out to different kinds of lines. How can I add all those things to the base plot that we have done? Then, if at all I have to plot some mathematical functions, right, like polynomial, some kind of polynomial functions, I want to typically plot. So, what is the kind of function that is available for me to do that job? Then, another important kind of plot that we will be spending some time on is the box plot. Very essential, especially if I'm looking at the distribution of the data. So we'll spend some time in terms of understanding the box plot. Then, if at all I have categorical variables, what are the other kinds of plots that I can look at wherein we'll be talking of bar chart, etc. And if we have only one single sample of data, what are the different kinds of plots wherein we would be talking about histogram along with a few other charts. If at all I have multiple variables, not just two, what are the different kinds of charts that I am looking at? Here is where we talk about the scatter plot matrices and quite a few other charts. And then we would move towards special plots, and towards the end we will see how do I save all these kinds of charts to a file. Let's say if I'm talking about a PDF file, how can I save all these kinds of graphs that I've created to a PDF file, right? So let's get started. So the main intention of this session is coming out with different kinds of high quality graphs, and that is what is the base for any kind of a statistical computing exercise, right? When we are talking about analytics, within which the first stage of analytics where you call as the descriptive analytics. So within that descriptive analytics, you see either we are going more and more in tabulation of the summaries, or it could be graphs and visualization of the summary. So one of the most important aspects of analytics, the base analytics that we are talking of, is coming out with very good visualizations of the data. So the type of the plot that you are going to go with is purely based on the number of variables that you want to plot and what is that you want to highlight. So the majorly it's the number of variables. So if you look at the kind of categorization I have done, if I have two variables, what are the kinds of plots that I need to look at? If I have a single sample of data, what are the kinds of plots I need to look at? If I have multiple variables, what are the kinds of plots that I need to look at? Now, this is how we would typically take our session forward. Now, if I have two variables, we'll get started with two variable scenarios. We'll try to execute them in R as well. So, in majority of the cases, the response variable is there on the y-axis and explanatory variable on the x-axis. Whenever we are talking about two variable stuff, so on the x-axis generally we have explanatory variable, on the y-axis we have the response variable. Now, depending on what is the type of the response variable and what is the type of the explanatory variable, we would have different kinds of plots. Now, if you see here, if this explanatory variable is a continuous variable, right? If the explanatory variable is a continuous variable, which means it's a numerical kind of a variable, and your response variable is also numerical, both of them are numerical kind of variable, what we are plotting is a scatter plot. Whereas if this explanatory variable is more and more categorical kind of a variable instead of numerical, if this is more categorical kind of a variable, either I would be going with a box plot or I could go with a bar chart. So there are two different possibilities here. If the explanatory variable is a categorical variable, then I can look at either a box plot or even a bar chart. So some of the functions that we have in R, so we can go with a plot depending on if X and Y both of them are numerical variables, then I would by default get a scatter plot. But if I have a plot wherein the first variable is a factor variable and the second one is a continuous variable, then the default plot function will give me the box and whisker plot of y for each factor level. And if I'm talking about a bar chart, if I'm using the function called bar plot of y, it is getting the heights from a vector of y values. Now let's look at each one of them. Let me look at each one of them here. So for that I'm just pulling one data from my system, right? The customer data. It is located in this particular folder, so I am trying to load that particular data. Quickly, if you want to do a basic checks, I am doing a dimension, right? These are some basic checks. So 300 rows, 7 columns. I'll do a head to understand what this data is all about. So you could see age, gender, income, kids, own home, subscribe, segment. Now we have a few quantitative variables which are continuous variables, and we also have a few factor variables. So it is very much comfortable for us to understand different kinds of plots on this kind of data set. So now let's say I want to first find out the relationship between two continuous variables, right? This is where I can use plot x comma y. So here let me take the relationship between age and income. I want to see, is there any kind of relationship between age and income? And you know, here both of them are continuous variables, so I'll try to do a plot customer dollar age, that is my x value, and customer dollar income, that's my y value, and plot is the name of the function that I'm giving. So this is the kind of a chart that is coming out, right? We'll discuss more and more about it, but initially we'll have a quick plot. So we could see that as the age is increasing, looks like the income of the customer is also increasing, looks like there is an upward trend. This kind of a chart is called as a scatter plot. For different values of x, we are plotting different values of y. And this is what we are calling as a scatter plot. Right, so if I'm using the plot function with both the variables being continuous variables, this is the kind of chart I'm going to get. Whereas on the other side, if I'm using the first variable as a categorical variable, so let me take the plot, let's say with respect to gender, right? Let me take gender as x, but the same income as y. So the first one is a factor, the second one is a scale. suddenly the chart that I am getting is a box plot. This is what we are calling as a box plot. I'll have a detailed explanation of the box plot in the next couple of slides. So this is how the box plot is coming out, which means the same plot function, depending on the kind of inputs that you are giving to it, it would typically change. Now similarly, if I'm talking about bar plot, right, if I'm going with the bar plot of gender, okay, bar plot of gender, sorry, bar plot of, yeah, bar plot of income. So what you could see is for each customer, different incomes are typically being plotted. So it's just a height from a vector of all the values, from a vector of income values. So for each person, I'm getting a separate bar plot. So for all the 300 people, 300 different bar plots associated with the income are plotted. Generally, this is done for the summaries. If I have done the average income, let's say segment wise, then I can have a quick bar plot. Probably let's look at this part, right? Let's say segment average income, right? Segment average income. So I'll use the aggregate function, wherein I will take customer dollar income tilde customer dollar segment, and the function I would take it as mean. So here if you see what it has given, segment average income, it has given the average income for each of the segment. Now what I can go with is bar plot. I'll take this. Means for each segment, whatever is the average, I have to take it as segment average income dollar customer dollar income, or probably let me take it as the second column. So let me take the second column. So this is how the bar plot is going to come, right? It is typically plotting for a numerical vector. A bar plot as a function gets plotted for the numerical vector in this typical manner. So either I can do it for the summaries or I can do for the raw data as well. Now, moving forward, the next point that we are trying to touch base upon is the scatter plot. And within the scatter plot, there are two ways in which I can get the chart plotted. There is a Cartesian plot way where I give x value comma y value, or I also have the formula plot way where I will capture the y value with a tilde sign and then the x value. So this looks more and more like a model, right? Within the model, any model that we create also we create in the same manner. The y being the response variable, we model it with a tilde sign, x being the explanatory variable. So typically when we are using the plot function, it looks more and more similar to that of a model. So that's the reason sometimes people prefer this kind of a plot compared to the other one. And by default, when I'm using the plot function, the axes are drawn and a scatter plot of the points is done. This is what we have seen earlier, right? When I'm going with this one, plot of age comma income, only this much. By default, when I'm using the plot function, I'll simply get the age on the x-axis and the income on the y-axis, and only a scatter plot of the points are typically being plotted, nothing more than that. So now I can start adding extra functions to it. I can add points more and more. I can add more and more lines, and I have different kinds of functions. These are the different functions that are available to really add something more to the chart. Now, even the arguments. Let's start with the arguments first, right? Let's say color. So right now by default this is shown in black. Now if I set color equal to blue, right, the blue I have to type in double quotes. Now these points will become blue. And let me tell you, there are so many such kind of color names that R understands. If you want to know what are the different names that it understands, you can simply type colors. So there are almost 657 different kinds of names it understands. Almost all the routine colors it understands by its name. So you can type any of those names quite comfortably and you'll get the color of your choice. Just quickly, if you see, you want tan 2, right? The same thing. Instead of saying blue, let's say you want tan 2. Now the chart is becoming with a tan 2 kind of a color. Or probably let's say you want it as violet red 3. So this is the way you are getting your colors. So R understands different kinds of colors by its name. So I can very well set the color like this. Then the next part is the x-axis and the y-axis. If you see, by default the x-axis is just the name of the variable, y-axis is also the name of the variable. But if you want, we can very well make it much better. So that's where we use the argument xlab. Xlab is nothing but label of x-axis, where we can simply set it as age or age of the customer, whatever it is. If you wanted more detail, you can set it more detail. Similarly, ylab is about y-axis label, income of the customer. So rather than just getting the name of the heading, name of the variable, I can very well get it much more better off like this. And even to this whole chart, if I want a title, this is what you can set using main. Main equal to, you can set age versus income. Income of the customers. Now this is how your chart has come. You see the heading is age versus income of the customers. The x-axis label is age of the customer. The y-axis label is the income of the customer. So the other point is, so you have set the color, you have set the x-axis label and the y-axis label. And in some cases, PCH will set the points. Right now they are slight small circles, right? Now, if I set the PCH to be any number, let's say between 1 to 20, right? Let's talk about 3. Now it becomes, all of them will turn into pluses. And if I change that to 4, all of them are changed into cross. So there are different kinds of representations with different PCH. Let's say I'm making it 16. They are turned into colored circles, not open circles, right? So these are the different kinds of things that you set with the PCH. And then other set of arguments that you provide are xlim and ylim. especially if you want some limits for the x-axis and y-axis to be set, right? So right now the x-axis is taking between 20 and 80. Similarly, y-axis between this and this. Let's say if I want the x-axis between 0 and 100, then I can set x-lim. X-lim is equal to, I'll set it as a C function, 0, 100. Now you see my x-axis would be a limit between 0 and 100. Similarly, I can set between y-axis as well. So I can make my graph slightly different by changing the axis as well. So these are some of the important things. I can add different kinds of arguments to my chart, right? And now let's say I want to add a line, right? I want to add a line which is a kind of a regression line. Regression line is the line that passes through most of the point, the best fitting line, the best fitting straight line that goes through these points, right? The point which is the line that is having the least possible error from all these points put together. That is what we call as the regression line. So if I want to add a regression line, I have this function called AB line, wherein LM is nothing but I'm fitting a linear model. I'm fitting a linear model between y1 and x1, which is nothing but my variable y and variable x. I'm trying to fit a linear model, and on the top of that linear model, I'm trying to draw an AB line. So let's try. So once the plot is done, then only I can bring in my AB line. So let's say this is my AB line, wherein I'm performing an LM function. On that LM function, I'm taking my Y variable, which is customer income, and tilde sign, and I'm taking my X, which is customer age. So this is the AB line. Now you could see this is the typical line that is getting plotted, right? So even this one you can very well make it. This one you can very well make it colorful by bringing in color equal to all those kinds of arguments to it, right? So that's one part of it. So by default, the scaling is done based on the automated values. The Excel will, the R will typically look at what is the lowest value, minimum value, and the maximum value, and based on that, the limits, the lower limit and the upper limit will be set. But if you don't want those particular limits and you want to set your own limits, then you can use your xlim and ylim values, wherein you have to give them within the C function, and you will get your own customized limits for x-axis and y-axis. And then if you set type equal to n, right, in case you are setting the type equal to n, then basically basically the graph is plotting all the data so that the axes are scaled to encompass all the points from all data sets. So let's say I'm going with two different data sets, right? Initially I have plotted this, then I have another data set. I'm trying to plot that as well, right? So just for the example, here I have plotted the income, right? Now to this itself, I want to add points. Let me add some new points, wherein I'll go with age. Here I don't have the income part. So let me do the other way. So if you look at, first let me plot age versus the kids, right? Let me take customer dollar age, customer dollar kids. So this is how it is coming out. Now to this, let's say I want to add points, customer dollar age comma customer dollar income. Let's say I want to add the income like this. Now this is where you could see none of the points are visible here because your y-axis is just 7 from 0 to 7, whereas the income is much higher. Probably just you can see income divided by 100. Even then the points are not visible. So let me take income divided by 1000. No. Income divided by 10,000. Yes. If I'm doing income divided by 10,000, I'm able to see a few points, but you could see that things are going away from the graph because this axis is not changing in R. By default, the axis is based on the first one itself. By default, the axis is based on the first one itself. Now, this is the place, if I have multiple things to be plotted on the chart, what I would typically look at is, I would initially not freeze the axis. And for that point, we will set type equal to n. So let me again get started with the plot. So if I set within this plot, if I set type equal to n, then the axis would keep slightly changing as per my requirement. Right? I can set the limits. So I can very well set xlim is equal to, let's say, C0 to, right, we are dividing by 10,000. So 0 to 15. No, this is age. So I'll set it 0 to 80. Then y limit I will set it from 0 to 15. So I'll do a fresh plot. Right? I'm doing a fresh plot out here. Now this is where I'll start adding the points. So now when I'm talking about adding the points, I'll put customer age comma customer kids, and this I can set it to color red. Oh, customer age, customer kids. Okay, so for different ages, this is how the kids are typically coming out. Then I can add customer age and income divided by 10,000. Now, okay, so this is what is coming out. I should have taken a different color altogether. So the whole thing will typically come up when I am initially setting the type to n, so that the axes are scaled to encompass all the points from all the data sets. So initially you can create a blank plot. After that you can start adding the different kinds of points to it. That's one kind of an improvisation that you can do with respect to your scatter plot. So we have already given the range in each of the cases. right? The x limit and y limit. Now, if I really want to find out the good way to the access values, I can very well take the x1, x2 kind of ranges, based on which I can very well find out what is my minimum value of x1, maximum value of x1. Based on that, I can very well give what should be the limit for my x-axis values as well as my y-axis values. And then comes the another important part, which is the legend. Legend is talking about all my graphs. So let me come up with a good chart. Right. So let me take this plot versus income only. Right, where I will go with. So this was my initial plot. Now for this, let's say I want to come out with a legend. All I have to use is legend locator 1. Locator 1, it is a very interesting parameter that you are giving into the legend function, wherein the plot will select where the legend should be placed. Right, locator 1 is typically, it is trying to identify where the plot has to be, where the legend has to be located. And you could see, first you will give the legend labels. If you have two different kinds, let's say to this itself, right, this is one, and the second one you are typically adding in terms of points, right, for the same age. Let's say you are adding kids multiplied by 10,000 just to bring, and probably you are setting the color equal to red. Okay, so these are the two things. So you have to differentiate these two things. Now this is where we'll bring in the legend. So what we'll do, again, this legend is also after the chart is plotted. Legend, you say locator 1, right, which means it will search for a better place. Where the place is present, that is where it will try to put the legend. Then you have to specify what each thing means. So the first one is black, the second one is red, right? So both of them are open circles only. So what is that? You can very well say, you can specify whatever is the black one. Black one is income, and the second one is the kids. Probably let's call it kids itself. So that is what is one argument that we are giving, which is the legend part. If you have different PCH, means which are the different shapes, then you can very well give those PCH numbers as well. But here both of them are open circles, so I don't need to give it. The colors, I have two different colors. So again I'll give a C function. One saying it's black and the other one saying red. Alright. So this is how my legend is given. So this is where I can very well move my cursor, and the moment I have given locator 1, this is what happens. Instead of it setting it somewhere, it will allow me to choose a space. So if I say this is the legend gets created there. Right, and yes, because I did not set the PCH, even the PCH needs to be set 1, 1. So then it will give me the PCH color as well. Let me try to do it again with the PCH as well. PCH equal to 1, 1, because both of them are open circles only. So this time let me set my legend again, overwriting it. So the black circle is income, the red circle is the kids. So if I set locator 1, That is what is the advantage. I can look out for an open space, and in that open space I can very well set my legend part. So that's one more benefit that we are going to get by using the legend function, right? We can set the graph more and more clearly. So PCH, as I have already discussed, it's 256 different plotting symbols available in Windows. Numbers 1 to 25 are commonly used. You can very well play around with them. If I am setting BG equal to, then I am actually putting a background color, right, within my plot. Right, let's say I'm taking this plot, again age versus income, and if I'm putting BG equal to LO, if I'm setting, so I can actually bring in the points color equal to red, BG Okay, let me just get back on that. So, but typically color is what is typically setting the border color, whereas BG is setting the background color. Now, I can also add text to my data, right, wherein I can simply put up what is the text that I want to display. Let's say here somewhere at this location I want to add some text, right, or probably here I have an open space, so I'll add the text here, right, customers age versus income, or I have some kind of an open space here, so let me start adding it. So I will have to specify 20, and I'll have to specify the location of Y here as well. And once I specify so let me simply take the plot for kids, that is easier for you to understand. Because we have a lot of open space there. Now this is the plot that we have. So here I want at, let's say, 60 and some 7, I want to add a text. So this is what I can do. Text, X is 60, Y is 7. The text is some ABC I want to add. Now this is how we get the ABC added. I have to specify my X location, Y location, and I have to give my text. That is what would typically be plotted as a part of the chart itself. And if I want my window to be resized, I can use this windows argument, right? If I set window 5,5, I'll get a smaller sized window, right? So if you set it a little bit smaller, if you want even more smaller, make it 4,4. You'll get it as a smaller window. So you can set the size of the window for any kind of chart that you are going to plot, so that your chart looks more and more better. Now, if you want to add few other shapes to the plot, right? So you can add some rectangles, you can add few arrows. So all these different kinds of shapes you would like to add to the plot. So the moment you give rect and you give left bottom, x left bottom, y bottom, x left, y bottom. So here probably let's say you want to add one rectangle to the chart here. So all you have to specify is x left, y bottom. So which means 60. Let's say you want to plot a rectangle like this here for some reason. So you have to specify 60 and 3 is the x left bottom, 80 and 5 is the y right bottom, y right top. So this is once you give that, let's say you are talking about a rectangle to this chart. So x left is 60, right? We are giving x left is 60 to this chart. Then we have y bottom 3. Then you have x right, which is 80, and y top, let's say, is 6. Now a rectangle gets plotted in this area. So from here 60, 3 to 80, 6, a rectangle gets plotted. So that's how I can add that kind of a shape, and I can very well fill with colors, shadings, etc. All these kinds of stuff. Right? The moment you are setting your rectangle, again I can set color equal to this, and all these kinds of stuff we can very well play around with. So if you just look at your function called rect, you'll get the clarity on what all it can do for you. So you are specifying x left, y bottom, x right, y top. Then you are giving the density of the shading lines in lines per inch. So if you are putting it, if you are not specifying it, then there is no shading line, a 0 value, right? And otherwise you can give some specific value which talks about the shading in terms of lines per inch. And the shading is also the angle wise, you can very well specify what is the angle of the shading lines. You can specify the color, you can specify the border color, all these kinds of line type. You can specify the line type. So the default is solid, but if you want you can change it to anything else. So that way the rectangle function will help you to add some more details to the chart. Similarly, you will also have arrows kind of a function, right, on the similar line. If you want to set some kind of arrows starting from some point to some other point. So here also you have to give the same thing, x0, y0, the starting point of the arrow. Then you have to specify x1, y1, right, which are the 2 points, the ending points of the arrow. So either I am giving the starting points and the ending point. So I have to specify the length of the arrow, the angle in which the arrow can be drawn, then the type of the arrows, right? When you are talking about the code, we'll have different types of arrows. And par is talking about the kind of color, the color we have to give to the arrows. So you could very well give, let's say in the same, if you want to set arrows, the x0, y0, right? Let's say I want to start from here and go here, right? So I'll set my x0 is 50 and y0 is 1. From 50, 1, I'll say my x1 is 60, x2 is 3. So I want to set this as the arrow. What else? Length, I don't need. Angle, but code is important. Let's say I'm setting this as code equal to 2 and color equal to red. A red arrow typically, so this is the code equal to 2 kind of an arrow. But if I'm setting it to code equal to 3, it's like a bidirectional arrow. If I set it to code equal to 4, okay, there is so the invalid arrowhead specification. So code equal to 1. Okay, it's already plotted. So it's one unidirectional arrows versus bidirectional arrows. You can very well plot, right, by specifying different locations for your x and y values. So arrows is also another important thing that you can add to your chart, right? Angle. So we can even add angle as well. Let's say 90. Angle equal to 90. So you will get it with this kind of a typical line, vertical bar with two square ends. So you could set different kinds. No, you have to set it as code 3. So you are setting it to different kinds of locations. You are putting different kinds of locations, different kinds of arrowheads. All that you can handle through the arrows function. And if you want a polygon to be created, even you can add your polygon function as well. Right, you can very well create your complicated filling shapes, and that too you can use a locator as well. So initially, if you can see, you can create locations using the locator 6. So let's do this. This is a very interesting. So let me keep a new variable called locations, where I'm talking about locator of 6, right? So I have to give 6 different locations here. Now that I have given locator 6, so I'll specify my 6 different locations. All my 6 locations are typically being specified, right? If you want to see, you can type in the locations here. My 6 locations have been captured. So the x and y values for each of my 6 locations have been typically captured because I have clicked my cursor at 6 different locations. So once I have clicked all of them, I can very well say polygon. Polygon locations, right? And I can very well set my color equal to green. So I can very well create different kinds of polygons. So that's a kind of a polygon that's going to come up because I have specified 6 different locations by using the locator 6. This is one way where you can draw your different kinds of shapes on the graphs, which becomes more and more interesting way of presenting things. Right, you can very well bring in different kinds of complexities into your plotting process. So polygon is a very interesting function where you can bring out your location by using the locator. Depending on whether you wanted a hexagon or whatever, you can very well bring in your locator, and after that click on the chart at different points. That would generate a list of values, display your list of values, and based on that you can use your polygon function as well. So that's how you can work out on adding more and more different objects, different shapes to the existing plot itself to make the plot look more and more interesting. Now, moving on to the next important aspect in this session. If I have to draw a mathematical function, right? Let's say I have x cube minus 2x. I want to draw this. Let's say between minus 2 and 2. Now this is where I'll take the help of my curve function. Curve will typically do the plotting from a particular point to a particular point and the name of the curve. I mean, whatever is the equation that I really want to plot. So if I am simply saying curve, right, I say x cube minus 3x, 3 times x, x cube minus 3x, I want to plot it between -2 and +2. So I get the x values between -2 and +2, and my curve is typically plotted, right? Or if I want to see curve x squared, I want to just check whether the parabola is coming out properly or not. -4 comma +4. So I'll get a kind of a parabolic shape, right? So I can very well get these kind of things plotted, right? If I say x cube, so this is how the x cube is coming. Or let's say I want right, you can go with the square root of x, but square root of x is not defined. Okay, let's do square root of x, wherein you will set between 0 comma 4. So this is how your square root function is typically lying for x between 0 and 4. Right, you can very well specify your logarithm function, log of x, but of course, so this is how your log of x function is lying. You can very well get all these kinds of curves plotted by using this curve as a function. And for whatever the curves, typically the usage of curves is once you already have your scatter plot, right? The basic use of the curve is, let's say I have a scatter plot which we have done earlier, right? Let's try to understand that. I'm trying to plot between age and the income of the customer. So I have a scatter plot. On the scatter plot, I can actually add different kinds of non-parametric curves to it. So wherein different kinds of curves can be added. So there are four common kinds of curves that we talk of. One, I can have a lowest curve. It's a non-parametric curve fitter. Right? I will use the lines as an argument. And based on the lines, I am typically looking at plotting this. Right? I'll take the lines as a function where I'll take the lowest, and within the lowest I'll take the dependent variable and the independent variable, and based on that we'll try to plot the curve. So let me first try to plot this scatter plot. And for this scatter plot, let's see the different kinds of curves that are going to come out for us. So what we will do is, so one is a lowest curve, right, which is a non-parametric curve fitter. The arguments, I'll provide explanatory variable and the response variable. So for the same, I can do a lowest curve. Then I could also use lowest. It's a modeling tool. This is also another kind of a curve. So where the model is first fitted, and based on the fitting of the model, so we are using lowest as a function between the dependent variable and the independent variable. Based on that, I would try to use the predict function to specify the vector of values for each explanatory variable. So basically, initially a lowest model would be predicted, and that model, so here if I am talking about age versus income, right, let's understand something. So lowest is a kind of a curve that is directly fitted. It's a non-parametric curve. Based on the age and the income, a curve is fitted, right? Let's understand these four non-parametric curves. So to plot all four of them in one single screen, what I can do is I'll make this kind of a setting. Par MF row equal to C2 comma 2, which means it's a screen wherein I'll have 2 by 2 graphs. So basically this is one chart, this is another chart, this is the third, this is the fourth. I'll get my 4 charts plotted here. So it's a 2 by 2, the plot containing 2 rows and 2 frames per row, 2 charts per row. Now that is how I can typically, so which is basically a 2 row chart and for that I have two charts per each row. So we can make that kind of a setting so that all four curves I can observe side by side. So I'll set par mf row equal to C2 comma 2, right? So my now the new chart that I am plotting, I'll not get the full space here, only have this much part of it will be my each of the chart. So now let me start the plot, the customer age versus the income of the customer, right? I'll take the age and the income of the customer. So this time first let's start with the lowest. So let me just call it as lowest curve. So this is the first one that we are plotting, age versus income. On the top of it, I want to draw a lowest curve, which is a non-parametric curve. So I'll take it as lines lowest. I have to give my explanatory variable, which is my age, and I would provide my response variable, which is my income. So this is my lowest function. So I can put my color equal to red. So my lowest curve gets created. So this is the non-parametric curve that gets created out here. Similarly, I will typically try to assess the lowest curve, which is a modeling tool. So there is a lowest model that is created based on my dependent variable and the independent variable. And after that, for different values of my explanatory variable, I'll try to predict the values of my response variable, and that is what I go with the lines function. So in the second one, what I'll do is I'll do a plot. The second plot I'll come out with this, wherein I will set my heading as lowest. So this is my lowest function, lowest curve I want to plot to this scatter plot. See how the curve is fitting to this particular scatter plot, because regression line is a straight line that is fitting this scatter plot. These are the different kinds of curves that I can fit to my scatter plot. So when I have to do it as the lowest curve, what I'll do is I'll create a model first of all, where lowest is a function, because lowest we said it's a modeling tool. So I have to take my y values, which is the dependent variable, tilde my explanatory variable. So this is what will give me my lowest model, right? If you look at the summary of this model, it has really summary. If you give the summary of this model, so it has it's a lowest function. So equivalent number of parameters is this much. This is the standard error. So this is the kind of function that it has created. Now if I have to use this particular model and try to create a plot right from the minimum value to the maximum value. So I need to know the minimum and the maximum values to do that. Right, so probably let me take the minimum value of the age of the customer. Right, or probably let me do it from 20 to 80 something. That would be straightforward. So I'll take my x variable to be 20 to 80, and based on that I'll take my y variable using the predict function. The predict function, the input, I'll take the model, and whatever the data that I have, the x variable, I have to create it into a data frame. So I'll put it as data.frame, and I will set customer $age is equal to the x variable. So What has gone wrong? Y variable, I am taking it as a predict for different values of x. Hmm. So if I look at the y variable now, so it has plotted, it has come out with, now this is the actual y variable. Now if I talk about the lines to the y variable, okay, it has to be a smooth curve. Let me just do again. So I got my model x variable. I'm taking the values between 20 and 80. For y variable, I am using the predict, right? And I'm using the model data dot frame. I'll set age equal to x variable. I'm creating a data frame with age equal to the x variable. Okay, new data has 61 rows, but variables found have, no, the new data is having 61 rows, fair enough. So now I will plot lines where I'll take x variable, y variable, and I'll set the color equal to red. X and x and y different lengths. What is happening? So if you talk about length of xv 61, length of yv is 300. Predict model, so something is going wrong with my yv data dot frame. Okay, let me say new data. Uh, Variables found have 300 rows. What is happening to my age 1? Age 1 is not there. XV, what is the values? These are the values that are associated with XV. So let me make it XV is as dot data frame of XV. So if I look at XV now, it's a data frame. So now let me use my Y variable to predict new data equal to XV. variables found. Why is this giving me this? Model. Now if I look at my YV, okay, these are the YV values that I am getting. Based on that, let me try looking at my lines function. Lines of xv comma yv color equal to red. They are having different length. Or let me plot it back to the data itself otherwise. Right, let me take new data equal to customer dollar age itself. Okay, now let me see. I'm taking it with the existing data itself. I'm doing the prediction. Then I'm adding the lines. Customer dollar age is my y variable. So my x variable, let me call it as customer dollar age. So this is the kind of a lowest curve that is typically coming up, right? Because I am trying to plot for each of my existing data itself, right? Let me do it again. For each of my existing curve, initially I came out with a plot, and after that I've created a lowest function, and based on the lowest function for each of the observations, we have again come out with the plotting of the same model against that data, and once that model has plotted, we have got a smooth curve like this. So that is what is coming out as a part of my lowest curve. Then I can move towards the generalized additive model based curve, right? Generalized additive model based curve I can plot, which is there as a part of the MGCV package. So let me install that MGCV package. So I'll go to this location, go ahead and install the MGCV package. So I'll use the GAM function, which is the generalized additive model function from this package. Even the GAM is also a typical model itself, wherein I'll take my dependent variable and I'll also take my independent variables. I'll have to do exactly the same kind of a process. And again, I have to use the similar kind of a mechanism. So let's say if the whole thing now with MGCV, let me try it. So I'm loading this particular package, right? So now the plot first. So we are doing the plot of customer dollar age. We are again going with the scatter plot customer dollar income. So, and this time let me call this as gap. So the third plot is coming out here, the GAM plot. Now again the same thing, I have to take my model. I am using the GAM function here. My dependent variable is customer dollar income. Right, if you want, just have a quick look at what the GAM function is doing. That is what we can give you the clarity here. Here you have a formula and you have family of distributions. So either you go with so we don't need all, we just need the formula here, that is sufficient. But of course, for the x-axis variable, you can very well specify the smoothened function of your explanatory variable, for which you can do a S of. So let me do a model where I am setting the GAM. The response variable I'll go with is customer dollar income tilde. My independent variable or the explanatory variable, I'll take it as a smoothened values of the age. So based on that, I'm trying to build a generalized additive model. So this is the model that I have got. Now, what I'll typically try doing is I'll do a predict, right? I'll use my y variable in this case to do a prediction of, based on the model that I had, I want to predict the list containing for different ages of the customer. I want to do the prediction for each of the ages of the customer. Object age not found. So again, let me use my predict function. I'll say new data equal to customer dollar age. Predict.gam. Not all required variables have been supplied in the new data. So it has to be in the form of a list. Let me just see what it is expecting from me in predict.gam. Object, new data. So that is a fitted GAM object as produced by GAM, and I am giving the new data. A data frame or list containing the values of the model covariates at which the predictions are required. It should be either a data frame or list. Then predictions corresponding to original data are returned. Okay, predictions containing the original data are returned. If new data is provided, then it should contain all variables for prediction. So let's original data only, let's try to fit. So which means I'll talk about my y variable as predict, and I'll simply say model. Okay, so I'll get my y variable values. So this is where I'll use my lines function, where I'll take the existing customer age, and based on that I'll try to compute my y variable, and I'll set the color to red. So even this kind of this is another line. This is a GAM curve that is typically being produced. So we could see that this is also a different kind of a curve. So these are different kinds of curves that we are modeling. Instead of straight lines, for a scatter plot we are trying to use different kinds of curves. And the fourth one that we are looking at is a cubic polynomial. So we'll use LM for polynomial regression. So we are fitting a linear model involving the powers of x. That's the only difference that we are doing in case of a cubical model. So again we'll do the plot, customer age main. This time I'll call it as cubic polynomial. Right, this is a fourth chart that we are plotting between the age and the income. So I'll plot a cubical model this time. So I'll use the same LM function, the linear model function, wherein my dependent variable or the response variable is the income of the customer. I'll take the tilde sign, wherein I will have to consider the independent variable, which is the age. To it I'll add the second layer and the third layer as well, the quadratic and the cubic part. So if I am doing that part, I just need to put the I function. I function is more associating with the identity kind of a stuff. So whatever is the squares, cubes I want to use, I'll simply include the capital I part. So this is how my variables get added, okay, along with a plus, not with a comma. So if I want to fit a cubical model, this is the way I try to fit my cubic model. Right, so this is the model that we are having. So based on this, I am creating my y variable, which is nothing but I am using the predict function of the model. So it is predicting back to the original data itself. Then I'll do my lines, wherein I have customer dollar age, that is my that is my x-axis. Y-axis I have my fitted values, and color I'll set it to red. So different kinds of curves. So these are the four different kinds of curves that we are getting, associated with four different curve generating functions on the scatter plot. I can use any one of them because sometimes instead of fitting a straight line to a data, it might very well be appropriate if I am fitting a curve to a data. So trying to understand different kinds of curves from the data so that we can do a much better exercise in terms of fitting an appropriate mechanism to understand the relationship between the explanatory variable and the response variables, right? Now we move on to the next important set of plot, which are the box plots, especially when my explanatory variable is categorical. Till now we have looked at the scatter plot, where the explanatory variable was more of a continuous variable. Here, when my explanatory variable is more categorical, I cannot produce a scatter plot. Now this is where we would be using the box and whisker plot, right? We'll have a detailed discussion of it. So I'll use the plot function only, but the first variable would be a factor variable, the second variable would be a continuous variable. So let me get started. Let me clear this off altogether. Right, even let me close this window as well. So let me do a plot. Now my categorical variable is customer dollar segment. For each segment, I want to look at the income. Customer dollar income. So this is where I am getting a box plot, right? So for each segment, moving up segment, this is the box plot. For suburb mix segment, this is the box plot, and so on. So any factor is having two or more levels. I can give that as my explanatory variable, and the response variable is a continuous variable itself. Look at the output of the box plot. So it is giving me a lot of information. Look at the dark horizontal line in the middle. That is what we are calling as the median. The horizontal line which is in dark is the median. So probably I can say that the median for urban hip is much lesser compared to the other groups, right? So that is what we are able to inference from the median. Then the bottom and top of the box. So this is the quartile 3, this is the first quartile. So quartile 1, quartile 3, this is what is mentioned by the box. So if the box is having a bigger height, it means that there is a huge variation between Q1 and Q3. But if the box height is much smaller, I can say that there is not too much of a variation between the quartile 1 and quartile 3. So it is the location of the middle 50% of the data. Then you have whiskers. This line and this line are typically called whiskers. Right here, if you see from here to here, here to here, there is a line. Right? So these are my caps. Now if I look at my upper whisker, it is either the maximum value, right? Here it could be the maximum value, or the largest data point which is less than 1.5 times the interquartile range above the 75th percentile. I'll tell you what it is. Okay, let's look at this segment, right? Because it has a few outliers. Or let me take this traveler segment, right? Or even the suburb mix, because we have both sides some outliers. So let me take the suburb mix segment. So the first thing I want to find out the maximum value, right? So let me take the aggregate. I'll take the aggregate of customer dollar income tilde customer dollar segment, and the function I would like to use is the max. I'll find the maximum value. Okay, the maximum value in the traveler segment is 114278. That is the maximum value, right? And in the suburb mix, it is 85,290. That is the maximum value. All right. Now, I would also want to find out my interquartile range, IQR. So the interquartile range in case of suburb mix is 13,187. All right. Then I would also want to find out the Q3, Q1 and Q3. So we will first find Q1. I want to find out my quartile 1. Okay, so for that I can take the summary. I want to find is it Q1? Let's see if quantile works. Yeah, I think it is the quantile function. So here I could see the Q for suburb mix, the Q3 is 61,315. Now what we are saying is, let me take this number 61,315 plus 1.5 times the interquartile range. This is my interquartile range. Alright. 1.5 times the interquartile range, which is 81,097. That is what is one value that I would be looking at. So whichever is minimum, I'll take the maximum value, which is 85,290. I will take the Q3 plus 1.5 times the interquartile range, which is 81,097. Whichever is the minimum, that minimum is what I would plot as a part of the whisker here. The same logic goes for your lower side of the whisker as well. So I'll take either the minimum value or Q1 minus 1.5 times the interquartile range. So here it is coming 28,000, and I would also look at the minimum values for each of them. Instead of the maximum, I'll look at the minimum value. So the minimum value here for suburb mix is 19,282. Whereas this limit is 28,346. So whichever is the higher of the two would be the line. So that is how my upper and lower whiskers are typically computed, right? So I will be taking Q3 plus 1.5 times the interquartile range or the maximum value, whichever is the lower of these two. That would be my upper whisker. And when it is coming to the lower whisker, I'll take Q1 minus 1.5 times the interquartile range or the minimum value, whichever is the maximum of the two. And any other values which are lower than this whisker, they are all treated as outliers. Now that's how the typical box plot indicates. So the points which are more than 1.5 times the interquartile range, above this upper above the Q3 or below the Q1. 1.5 times the interquartile range, below the first quartile or above the third quartile, and they are all highlighted through circle. So if there are circles as a part of any of the box plot, it indicates that there are outliers in the data. So when there are no outliers, whatever it is pointing is typically the maximum value itself. If you try to look at, let's say for the moving up segment, the same thing, there is no outlier, right? The minimum value is 29,000, and if you look at the calculation, the Q1 minus 1.5 times the interquartile range. This is the interquartile range. So you'll get it as 28,000 something. Whichever is the maximum of the two. This is what is the maximum of the two. So this is what is typically plotted rather than this. Whereas in the earlier case for a suburb mix, this was the highest of the two. So this was plotted compared to this. So the remaining things were being shown as outlier. So this is what is typically coming out through a box plot. So it shows the location and spread of the data. So location in terms of median, spread in terms of interquartile range, and as well as skewness, right? How much these are the points across the median. So if you look at here, more or less points are equal above on the upper side as well as on the downside of the median. Whereas if you look at it here, from here till here is the upper side, whereas from here till here is the downward side. So you could see slightly skewed out here. Even here, if you see, the median is here, the upper hinge is here, the lower one is here. Slightly, you could see there is a slight variation. So there is a little amount of skewness that is present in the data. So this is one more way. Probably if I want to look at the skewness in each one of them, then probably I can very well use some other functions to determine, but using a box plot to determine the skewness is done through this mechanism. So it is one of the good tools, especially if I want to look at the errors when there are extreme outliers present in the data. right? So it does not compute any kind of parameter. It is completely a non-parametric plot because it is taking the medians, the interquartile range, which have nothing to do with the computation, but their relative positioning in the ascending order or in the descending order of the data. So it does not compute any kind of means, any kind of standard deviations in the process. In some cases, we can also look at going for box plot with notches. So when we are doing a box plot, we can simply set notches equal to true. The same box plot, right? Let me use again the plot function with the only change being notches equal to true. Right, when I am setting the notches equal to true, actually the notch is getting computed as the way the notch gets computed is plus or minus 1.58 times interquartile range divided by square root of n. That is the way the notches typically get computed, especially when you are looking at the box plot. They are typically not good whether when they are explaining whether or not the median values are significantly different. Now you could see here the median of this is different from this. Median of this is different from this. But there is no way where it says it is significantly different from each other. Now this is where the notches are coming into picture. The more, if I am able to plot the graph with a notch, then at least it is going to tell me whether the notches are overlapping or not. So the notches are typically drawn as a waist on either side of the median. So instead of a median getting plotted like this, the median will get plotted more like this. It's a kind of a waist that is coming on either side of the median, which will give me a rough impression whether the two medians are significantly different or not. And by default, the 95% confidence interval for the difference between the two medians is typically plotted. So I can very well set this. Let me see why it is not coming up for this data. I think I have to use box plot as a function. Let me just check that. Instead of plot, so box plot says I have to give a formula y and tilde the group. So I have to give within this is notch equal to false or true. Okay, I have to give it like this. So let me use box plot. I'll take y, customer dollar income is my y value, tilde customer dollar segment is my x value. So I'm taking the formula, right? So I'm taking the formula out here, then the data, anyhow I have taken it inside. Then I have to very well specify the notch. So I will say notch equal to true. If I set notch equal to 2, yeah, this is how I am getting my box plot with the notches. Now if the notches are overlapping, then I say that there is no significant difference between the medians. So here the notches are overlapping. So I can very well say that there is no significant difference between the medians out here. In this case also you could see the notches are typically overlapping because this one is here. So the notches are overlapping, so there is no significant, the medians are not significantly different here. Whereas here if I could see the notches are not overlapping. So I could very well say the urban hip is the average, the median income of the urban hip is comparatively lesser to all other groups, because what the notch will typically compute is the 95% confidence interval for the difference in the two medians, and it is typically computed as 1.58 times interquartile range divided by square root of n. So based on that, the hip is typically getting computed. So the boxes in which the notches are not overlapping at all, for those boxes I say that the medians are significantly different. So it is a kind of a test, the test of significance that is associated with the medians. So instead of performing the test, I can use the box plot with the notches so that I can compare across the plots quite comfortably. And if there are overlapping notches, for all those I will typically make a conclusion that there is no significant difference in the median. So you could see as the formula wise, as the interquartile range is increasing, the width of the notch is increasing, and as the sample size is increasing, the width of the notch is typically decreasing. The more and the more sample size that is coming out, the width of the notch is typically decreasing. On an average, this is the typical formula to compute the notch, and the box plot is plotted with respect to the notches in this particular manner. Alright. Then, if I am looking at other categorical variables, I can very well rely on a bar plot. So it is talking about the heights of some values. It could be mean, it could be a standard deviation. So from different kinds of aggregates. So I could very well compute the aggregate across different segments. So I will look at customer income across the customer segment. I'll take the aggregate. Let's say the aggregate I am talking of is the mean. So this mean I can very well plot as a part of my bar plot. I can take the mean as a part of my bar plot. So I'll take this aggregate function. Out of this, I'll take the second column of this and I plot a bar plot for this. So this is how the mean values are coming for each of the segment. So I'll get a bar plot of the means. So same way I can compute any other. Let's say I want to look at the interquartile range. So all I am changing is, instead of mean, I am putting it interquartile range, and I am again plotting the bar plot. So bar plot is typically taking the y values, which are the quantitative values across each of the segments, and based on that the chart is typically getting plotted. So the heights of the bars, I can very well compute them either using t apply, or we have used aggregate here. So any kind of a function through which I can get my heights of the bars, and based on that I can simply get those bars plotted. And I can put my x label, y axis label, the colors, all those kind of stuff. And in some cases I can have the plots for multiple comparisons, right? When there are many levels of a categorical explanatory variable instead of one single explanatory variable, if I have many layers of a single explanatory variable, we have already looked at that the box plot with the notches, that can typically compare whether the medians are significantly different across the groups or not, right? But the other one that I can very well look at is Tukey's honest significant difference plot. Very interesting plot. So I have to go with, first of all, a model. The model is based on the ANOVA. So I'll create a model wherein I'm talking about the response variable, versus the factor variable, right? I'm taking the response variable versus the factor variable. So if you look at it, I'll create a model where I'm using, this is AOV is what is an ANOVA model. I am creating the response variable versus the factor variable. So this is what is my ANOVA model that is getting created. And on the top of that model, I want to plot Tukey HSD of that model. Tukey HSD. Plot Tukey HSD of that model. So this is the kind of a graph that is going to come up. For each of the segments, now I could see the difference in the mean levels across each of the pairs. Right? Now for each of the pairs, you could see urban hip minus the travelers. This is what is going to be the value. So you could clearly see, or probably now to see the text to be much better, I can very well set las equal to 1, right, so that the text looks horizontal. So if I want the text to be horizontal, I'll set las equal to 1, and probably it's better that I set the margins as well because it is losing out on the space. So I can set the margins as well so that I can look at the graph much better. So let's say on each side, right, on first this side I can set it as 5%. On the second vertical, this is the vertical, so I'll set it as 10. The third one I'll leave it as 5, and the fourth one also I'll leave it as 3. So the margin is not coming up. So let's see here. The plot is not taking the margin, but otherwise you could clearly see that this is nothing but the difference between the first one and the travelers, the first one and the suburb mix. So it is typically coming up like this. If you look at moving up versus suburb mix, moving up versus travelers, moving up versus urban hip. Similarly, suburb mix versus travelers, suburb mix versus urban hip, then travelers versus urban hip. So these are the typical differences that are coming out. And now you could clearly see wherever the zeros are getting overlapped. If you see here moving up versus the suburb mix, you see that there is an overlapping zero. So this says that there is no significant difference between these two groups. So wherever the zeros are overlapping, I could see that there is no significant difference between the groups, and wherever the zero is not getting overlapped, I say that there is significant difference between the groups. So probably if you look at this one, this is urban hip versus moving up. This is urban hip versus suburb mix, and this is urban hip versus travelers. So these are all much away from zero, saying there is a significant difference between these groups. Whereas here, if I am looking at, in this case also, there is a significant difference, but at least between suburb mix and moving up, this Tukey's HSD model is not showing any kind of a difference between the groups. So comparisons having the interval that do not overlap the vertical dashed line, that is the zero line, they are all significant. So in this case, they are all significant because only this one is not significant. In all the other cases, the differences are pretty much significant. So that is one more chart that we can very well use, the Tukey's HSD graph, especially for comparing the significant differences in the mean values across the group. Remember, your notched box plots are comparing the medians across the groups, whereas Tukey's HSD on a significant difference is comparing the mean values across the groups. So that is one more kind of a chart that you can rely on, especially for your two variables kind of categories. So these are all some of the important graphs addressing the two variable scenarios. All right. Now let's look at the different kinds of plots you have for single variables. Right, till now for two variable scenarios we looked at the scatter plot, we looked at box plot, we looked at the bar chart, right? We also looked at the box plot with notches, even the Tukey's HST. These are all different kinds of charts that you can plot with two variables. Now, if there is only one variable, the first thing that comes to my mind is the histogram. Especially this variable needs to be a quantitative variable or a continuous variable. So it's a histogram which is primarily showing the frequency distribution. So I'll go with the histogram using the hist function. I'll use the hist function for my histogram, wherein I'm taking customer dollar, I'll take income. Because it's a quantitative variable, I'm looking at the histogram. So this is what is the distribution that we are getting out of the histogram. Right, for each one, again I can use color, all those things. So if I am going with a histogram, this is what is the plot. If I use simply plot function, if I am using simply the plot function, it's actually an index plot. If you look at plot of customer income, so it will take the sequence of observations on the x-axis and each individual observation on the y-axis, and it just gives the plot 0 to 300 observations. For each one it is typically giving me the plot. So that's how the plot is working. And if at all I have a time series related data, these plots we'll talk about slightly later. So if at all I have a time series related data, then I can use it as plot.ts of pi. Right, this is purely when my data is more and more time series in nature. And if I have a pie chart is primarily associated with a circle, and within that dividing the elements into this. So if I'm talking about pie chart, again there's no meaning to the customer income, right? But it would be more and more comfortable because X value must be positive, or there is some place where income was not positive, looks like. So let me look at some other variable. So there's no meaning to it, but this is how the pie chart gets plotted if the data is too huge. Or I could have gone with aggregate, right? Probably that's a much better thing to do, right? I'll use the aggregate function. I'll do a pie. Within that I'll use the aggregate function, and within that let me take the second column. That would be much easier for a pie chart. Looks better. So this is my first group, second group, third group, fourth group. So when I want to really divide the data across the various groups, this is where I'm resorting to a pie chart, right? Then looking at the histogram versus the bar plot, right? Earlier we have looked at the bar plot where we had two variables, whereas in histogram we are talking of one variable itself. A few important differences for the histogram: you have the response variable on the x-axis, and the y-axis is purely the frequencies of how many times each range values have occurred. So this is how your histogram was coming out, right? If I look at the histogram, so this is a frequency of values on the x-axis, and how, sorry, this is the range of values on the x-axis where your variable is there, explain where the whatever is the variable, and on the y-axis we have the frequencies, how many times this particular occurrence has come within a particular range. So that is what was depicted by a histogram, whereas for the bar chart you always have the response variable on the y-axis and categorical variable will be on the x-axis. So that's one major difference you could see with respect to the histogram versus the bar plot. For the histograms, you first of all require the bins, right? Bins are nothing but those divisions of the x-axis. Now, I have the x-axis containing the list of incomes, right? The whole incomes of the customer. That is my x-axis. Now, I want to divide that x-axis into the values to show how they are distributed. And within each range, I want to count how many occurrences are there. Now, depending on the number of bins, my shape would be completely different, right? If my number of bins are, so by default, this is the number of bins, right? But if my number of bins are more, my histogram will look slightly different. If my number of bins are lesser, my histogram looks completely different. Now this is where I can have the histograms completely different based on the bins, right? I can specify what are all the bins, and based on that specification of the bins I can get my histogram created. So let's try that out, right? Histogram, if I set within this histogram bins equal to 20, okay, or probably I should set, first of all let me let me just check how do you specify the bins in a histogram. Okay, I have to give it as breaks. So breaks is a vector giving the breakpoint between the histogram cells, right? Or, okay, there is nothing called bins here, we are calling it as breaks, right? Frequency is equal to null, a function of the computer vector of break to compute the vector of breakpoints. So I can either compute the vector, so a single number giving the number of cells for the histogram. Oh, probably we can give this. We can give a breaks equal to, instead of cut equal to, or instead of bins equal to, we'll call breaks equal to 20. So I'll get 20 different breaks. So my histogram will look slightly different. If the same thing I make it as 50 breaks, my histogram will look slightly different. Now this is what we are trying to say here, right? Depending on how many bins you are trying to give, the histogram shape is going to differ. What you see depends on the subjective judgment where your bins are typically put. So small bins, they produce multi-modality. If you look at here, the bin size is very small, so there could be a possibility of multi-modal stuff. But if the bins are much bigger kind, then there is a possibility that you will have unimodality. Now, if you want to identify your bins, you can use the cut function. Take a continuous vector and cut it up to the bins you can use for counting purpose. You can define your bins, and cut as a function can very well be used to define all your bins. So the major advantage of using this bins is, or bins and histogram, primarily I am interested in looking at the mode, which variable, which range is coming out with more and more frequency. I can look at the spread of the data, what is the range in which the entire data is lying, what could be the minimum and the maximum values. And I could also see whether the data is more and more symmetric or skewed towards the left or skewed towards the right. So these are some of the important things that we can assess by looking at the histogram. Another powerful tool for making different kinds of assessments regarding one single variable. So, especially if I am talking of integers, I can very well set my breaks. We have already seen how to set the breaks. Breaks equal to something, I can set all the different kinds of explicit breaks. We have seen breaks could be set just as a single number, or probably the other way of setting the breaks is I can have the breaks from something to something, right? I can even I'll use a sequence function, right, where I'll have the breaks from 0 to 10,000 by 1000 each, or probably I need up to 100,000 by 2000 each, or let me take by 5000 each. So that's how I'm setting my breaks. So I can give breaks even in this way. Breaks do not, we have something more as well. So let me take it as 120,000. What about oh, there is a negative number as well. Oh. So let me put minus 10,000. Yeah, now it is coming because I need to I need to know the minimum and the maximum values. So I had some negative numbers as well. That's the reason it was not doing the job. So I can set it from minus 10,000 to 130,000 as the breaks with an increment of 5,000 each. Based on that, the breaks would be generated, and based on that, the histogram could be generated this way. So these are all different kinds of charts that I can go with. Then the index plot, as I have already discussed, whatever the values that I have, that would be plotted on the y-axis, and x coordinate is typically a serial number. So I can simply use the plot of customer dollar income, right? So each observation would be plotted with a circle, and it's a sequence of observations from 0 to 300. So primarily for error checking, are there some abnormally higher values, abnormally lower values? They could be quickly checked out by using this index plot. And if my data is more and more of a time series data, right now we are not talking about the time series data. So but when the data is more and more of a time series data, it can give me a kind of a quick plot talking about across the time how was my data moving. So if there is a very straightforward kind of a time series data, even a simple line chart will do the job. But if there are so many missing values in the time series, I should rely on one of these functions. So when I take the time series data example, I'll be covering these ts.plot and plot.ts function. Then moving on to a pie chart, we have already talked about for a proportional makeup of the sample in the overall presentation. So I want to do a breakup of the total into individual components. That is where I can very well use the pie chart. So it takes a vector of numbers, it converts them into proportions, and based on that divides the whole circle and allocates the proportions across the circle. So these are different kinds of charts that we can typically plot on your data. Very useful for single sample kind of plots. Then you also have a strip chart which is on a similar lines, especially if I am having samples which are too small in size, where box plot may not be of much of a use, because box plot computes median, Q1, Q3, outliers. So box plots are typically more appropriate when your data is too large, but if the data is too small, I can very well rely on the strip chart. Now the way the strip chart gets plotted is I have to give my response variable tilde my factor variable customer dollar segment. So you get strips. So you could see at least which of the variables are close together or which of the values are away. So you could see here in the traveler segment these values are much away from the others, especially these two, much different from the rest on the lower side, right? This is also slightly different. Even this point is slightly away from the rest in case of suburb mix. These 1-2 points are also not working well with others. So at least the strip chart will help me to identify the outliers more easily. So look carefully at the location of the individual values within the small samples. See by how much extent they are varying across each other. So I can get the strips as vertical or even horizontal. I think I can, this is where I'm getting the horizontal ones. I could even make them vertical as well. Right, probably if I can set, let me see if horizontal is equal to false. No. So let's check strip chart. Vertical equal to true if I set, not horizontal. In some cases for box plot you have to use horizontal, whereas in strip chart I'll use vertical equal to true. By default it is false. So if I say vertical equal to true, I got a vertical kind of a strip chart. So I can use the things accordingly. Then the same logic, if I want to test the normality of the data, then I can use a QQ plot where I go with the QQ norm. QQ norm, I go with the income. So this is one more chart which will do the normality test. So you could see here, this is the kind of a curve that is coming out, right? Which is if I see that it's a 45-degree line, then I expect the data to be more and more normal in nature. But if this plot is not on that 45-degree line, the more and more away it is moving from the 45-degree line, then I can very well say that it is no more closer to normal. It is much deviating from the normal distribution. So this is one way you could check whether the data is more close to normal or not. Though you have some other kind of tests, right? When we talk about the tests, we'll do a statistical test which ensures, which says whether the data is more and more normally distributed or not. So in this case, because it's not across this 45-degree line, I cannot say that it is more normal. You see, it's not a straight line kind of stuff. You see a lot of curve that is happening, which means it's not too good to be considered as a normal kind of a data. Then the next important topic that we are looking at is the plots with multiple variables. So till now we have focused on the plots with two variables. We have looked at different kinds of plots, right? We have looked at the plots with a single variable, right? In a single variable we talked about the histogram primarily, then the index plot, then we have also seen the pie chart, then the strip chart, right? So all these are different forms of the single variable kind of charts. Even the normality charts, they are all based on single variables. Now if I have more than two variables, multiple variables, and I have to do a plotting for them, this is where I would be using the pairs function. Pairs is a function which produces a matrix of scatter plots, every variable against every other variable. So if you see simply, you just do pairs and you give the whole data frame to it. you get a scatter plot between every variable and every other variable. In many cases, it may not make any kind of a sense because many variables are categorical variables, right, factors, whereas only a couple of them are really quantitative variables. So that's where you could see the only for let's say between age and income, I could see something better with respect to my scatter plot, whereas all other things it's not making much of a sense. But from an understanding perspective, yes, pairs is a function which is producing a matrix of scatter plots for every variable against every other. So you could very clearly look at what is the level of dependencies that are existing between the explanatory variables, all of them put side by side. So every variable in a data frame, it would be picking up whether it's a factor variable or a quantitative variable, whatever it is. So corresponding to that, taking one of them on the x-axis, the other one on the y-axis, all the pairs are taken. You could see the first is age, then the second column is gender. So every pair is typically taken and a chart is typically plotted. So the whole data frame is what you are giving as an argument. And there is an option to add non-parametric smoothers to the scatter plot. If you want, just like the way we have added curves earlier, right? Either the lowest curve or lowest curve or GAM curve or cubic modeling kind of a curve. All these kinds of curves, if you want, you can very well add them as an optional parameter. So this is one more kind of a mechanism, right? I can very well go with, let's say if I want to add that, I'll simply say pairs. I'll give a data frame, customer, and to this data frame I can very well say panel. This is where I'll add the smoothness if required. So I'll say panel dot smooth. The smooth curve is what I can bring out by doing this panel dot smooth. Now you could see across, because there's not too much of data, so here you could see there is a data, so you could see a smooth curve that is coming in this way, whereas for all other things, because they are factor variables, there is no meaning that is coming out to the smooth end curves that are getting created. Then moving on to the next function in the same multivariable kind of a category, we have the co-plot, another interesting plot. It's actually a conditioning plot. So we are talking about relationship between y and x, but for different values of z. What does that mean? I want to look at the relationship between income and age, right? But for different values of the segment. So for the first segment, I want to look at relationship between income and age. For the second segment, I want to look at the relationship between income and age. That is where I'll use the co-plot function. So if you see here, co-plot, I'm looking at the relationship between the dependent variable is, the response variable is this one, and I'm looking at tilde, the independent variable, which is customer $age, but I'm putting it with a pipe symbol saying this has to be paneled or this has to be a condition based on customer $segment. This is what I want as a part of the co-plot, right? And probably I can see a smooth end line also. So let me set panel equal to panel dot smooth so that I can see how this relationship is changing in each of the cases. So now you could see this is a moving up category, wherein the relationship is more like this. This is how the distribution has come out. Whereas the next category, if I'm saying, it has to be read like this: the moving up category, the suburb mix category, then comes the travelers category and the urban hip category. So this is how the overall plot got splitted up. So this is what we are calling as a co-plot, right? So especially if there is a multivariate data, there is a lot of difficulty because the relationship between two variables may be obscured by the effects of other processes. That is where this comes in more and more handy. I want to look at the relationship between age and income, but separately for each of the customer segments. Or let's say I want to look at age and income, but differently for each of the gender. So for females, this is what is the relationship between age and income. After a certain point, I see that there is a fall that is coming because this is the smooth curve that I am looking at. So there is a kind of a fall after a certain age, whereas in case of males, it's looking like as the age is increasing, the average income is also typically going up. So these kind of stuff is coming out much better. Probably if I look at the other variables, right, own home. So for people who do not own a home, it is looking like as the age is increasing after a certain point, there is more or less flattened out. Whereas for people who are owning a home, as the age has increased after a certain point, also the income is slightly on the upward path. So I could see different kinds of relationships. Coplot is primarily helping me out in defining those kind of relationships between two variables conditioned on a third variable, right? So I'm putting the response variable tilde the explanatory variable, I'm putting the conditioning variable, and if at all I want a smoothened curve also on the top of it, I can say panel equal to panel dot smooth. So panels are ordered from lower left to upper right, right? So this is how the panels come. Oh, lower left to upper right. Okay. So probably if I'm going with the segment wise, so then this is the moving up segment, right? It goes to lower left to upper right with the values of the conditioning variables. So 1, 2, 3, 4. So that's how the grouping is typically occurring. Overlap between the various shingles. If there is a too much of overlap that is existing between the various shingles, it shows how much of overlap is there between one panel and the next in terms of the data point. So there is a lot of overlapping between the data points that are there in common. So that's one way we can interpret the coplot, which is actually plotted between the multiple variables at one single time. Then we have the third set of plots, which are also called as XY plots, or we also talk about interaction plots. A set of panel plots is what we are talking of. So if you see here, the response to one factor depends upon the level of another factor. So I am giving one factor on one variable, right? So first factor is here, the numerical value is here, but at the same time I am plotting it for another factor out here. So basically if you see here, I want to find out the interaction between the gender and the segment. Two variables I am pulling together. So I'll take segment on one variable and gender I can use it as an interaction variable. Now that is how I have to give the input. If you see here, I will first give the factor 1. Factor 1 is the one that comes on the x-axis. So here I'll take the segment on factor 1. Factor 2 produces the family of lines. So I'll take the gender as the factor 2, which produces the family of lines. And the factor 3, or probably the response, is the variable that I am typically looking at having. So let's look at that interaction dot plot to understand it better. The first factor, I'll give customers segment. Then the second factor, I'll have to give it as customer gender. And the third factor, I'll have to give it as customer income. So this is how the curve is coming. Now across the four segments, now it is showing the straight line, the solid line is for a male, So I could see that for the males, the numbers are lesser across compared to females, whether in any of the four segments. In all the four segments, I could see that the average customer income is on slightly on the higher side for the females compared to that of the males. Now, this kind of interaction effect is typically possible through your XY plot or an interaction plot. It's a very good, effective graphical means of interpreting the results of your different factorial experiments. You have done using, let's say, one set of fertilizers versus the other set of fertilizers. You want to evaluate how effective is one with respect to the other. All these kinds of things can quite heavily handled using your XY plot or an interaction plot. So different kinds of plots with multiple variables which really help you to analyze your data more and more comfortably. Then you also have a few special plots. So one is the design plot, very interesting plot, which you typically use this function called plot.design. It's one of the very important ways of visualizing the effect sizes in the designed experiment. So which effect is heavily impacting the response variable versus which one. So I could see here, I'll take a response variable. I'll take two or three different kinds of factor variables. Right. So let's see this plot.design. Right. The response variable, I'll take it as income. And I'll look at it as, first let me look at the segment star. Another factor variable I can take gender. Another factor variable I'll take own home. So I'm taking three different factor variables, but of course I have to link all of them through stars. So I'm putting the interaction effect between the various factor variables. Now you could see the male versus female, the mean of the customer income is pretty minute. So the gender is not impacting the customer income heavily. Owning versus not owning also, the gap is not too heavy. But if you look at travelers versus the urban hip, the gap is looking quite drastic. Now that is how we can very well analyze the interaction effect that is present between the various graphs. Right, which variable, which factor is impacting your response quite heavily compared to the others. So the main effect of each of the factors with respect to your response is displayed. So the one that is having a big vertical line is having a very big impact on your response variable compared to the other ones which are very small vertical lines. So the default is the mean, but I can very well go and plot the others as well. Now if you quickly look at plot.design, right, if apart from, you could see here when you are plotting X, so it is plotting univariate effects of one or more factors, typically for designed experiment as analyzed by AOV. Now in case of fun, by default it's mean, but I can go with any other stuff. So by just setting fun equal to something, I can very well go with, let's say I want to go with the median. Now even in this case you could see female and male, own yes, own no, there's hardly anything. But travelers versus urban hip, the gap is much wider. So that's how you can very well compute the stuff, and based on that you can make your analysis of the data, especially if you're talking of the impact of multiple variables that are coming on it. Or you can create your own functions as well. Wherever there is a fun, either you can use the existing functions or you can use the newer ones as well. Then if there are many identical values that are existing, then I need to have some kind of a mechanism. So here let's say I am doing a plot right, with so many identical values. So let me take the identical values as kits, customer dollar kits on one side, and let me take customer dollar segment on the other side, right? So here you could see almost very few plots are shown because they're all identical values that are existing. So you don't find the plots are, I mean, because though there are 300 observations in the data, hardly I could see 7, almost 20, 21 plots. What happened to the rest of them? Because they are falling, two or more points are falling exactly in the same location, and all the repeated values are simply hidden. So you could see that this plot is not showing anything big. That is where I can take the jitter of both of them. Jitter, if you look at both of them, so the customer dollar kits, you put a jitter around it, and for customer dollar segment also you put a jitter around it, where you find small deviations being created. So it has to be numeric, okay? So because X, okay, the jitter kits is anyhow numeric, but I want the segment also to be numeric. So what is that I can do? I'll do as dot numeric as dot character customer segment. First let me convert it into a character, and once it became a character I'll convert it into a numeric, and on the top of it I'll apply the jitter, right? Mm, why is this not coming? NAs are introduced by coercion. First, let me see what is coming out through as numeric, as character, customer segment. So all NAs are coming. Why? Let me just check what is there coming under customer dollar segment. So these are the ones that are coming up, right? So I have to convert them. So if you say directly as dot numeric, and if I put customer dollar segment, what is coming out? Okay, so as dot numeric, if I put it, so I don't need as dot character again. So I can simply put as dot numeric itself. I think that is what was the scenario. So let me just pull this up again, the plot. So I don't need, so in the jitter, I don't need as dot character separately. So let me not convert that into character. So let there be as dot numeric only. Now this is how the jitter got produced. Now you could see what the jitter is doing is, within the plot function I'm using the jitter function. So what it is doing is it is increasing or decreasing the x and y coordinates by a very minute random amount. So slightly plus or minus, so that each of the point is shown separately. Now the more and more thicker the point is, the more it is easy to visualize. So the jitter here is very thick, which says, right, if you look at majority of the people who are in the third segment, which is the traveler segment, they have 0K. And then majority of the people who are there in the suburb mix segment, I could see that they have 1K. So the thickness is clearly telling who are falling in which kind of a zone. So that's the advantage that you get using the jitter. And similar kind of a thing can be very well used for your sunflower plot as well. Even in the sunflower plot, you will do the same thing. So you'll do a sunflower plot where you can give both of them. Customer segment, I think even this has to be numeric. So let me give as dot numeric customer segment, and at the same time let me give customer kits. So you could see different kinds of sunflowers coming up. Each layer is a petal. So more and more dense the sunflower is showing, the more is the concentration of that particular value which is repeating more number of times. Here you could see that the customers, there are three people who belong to the moving up category having 5 kits. There are 5 people, these are different petals. So the petals will show how many times that particular value is repeating. So produce one petal of a flower for each value of y that is located at that particular point. So single values are shown without any petals. 2 points have 2 petals, 10 points have 10 petals. So that's so here you could see it's only 1 point. Here also it's 1 point. So there is no petal here, which means it's only one occurrence where you have people in the urban hip category having 4 kits, or people in the moving up category having 7 kits, whereas people in the suburb mix category having 6 kits, there are 2 such kind of people. So this is how a sunflower plot also can do a good depiction of your data. So that's different kinds of charts that can really help us in doing the analysis of our data more and more comfortably. Right? Different visualizations of the data can be done using different such kind of graphics tools. But now the final step is, if you want to save your graphics to a particular file, you first give the path of the file. You say PDF, give the path of your file, and say file.pdf, whatever is the path, and then set it as file.pdf, whatever is the file name, .pdf. Set the width of that PDF, set the height of the PDF. That's the first thing. Then if you want, you have to decide how many rows and how many columns you require. Let's start doing it. Right. So let me create a PDF wherein I'll simply go with, I'll have to give my path. I'll give my path. So let me give it for the time being h colon, then graph.pdf. So that's the name of the file I want to give. So I'm giving a path this much, where I'm setting my width equal to some 5 units and length equal to some 10 units. So this is the kind of PDF I want to create, and I can very well think of what kind of plot I want. So you can create, sorry, it's not length, it's height. So for PDF, the width and height, not the length. Okay, so we are creating a PDF, right? In that, if you really want more number of, if you want number of frames per row, then you can very well set par mf row equal to whatever. So you can set 2 rows, 1 row, whatever it is. Then the major thing is you are typically plotting all your charts. Let me take par mf row equal to C of 2 comma 1. So we'll have 2 rows and 1 column in my PDF file. So I'll do 2 plots, right? So probably I can do the same sunflower plot. I'll do it as 1. I'll do a sunflower plot, and let me also plot the jitter. I'll plot the jitter as well. So I've plotted the 2 charts, and finally I can simply say dev.off. Dev.off is I'm closing the scenario. Now this is how you could get, so your overall thing is typically saved off, so you can very well open your PDF file and have a look at it. So look at my PDF file. Here I have one of that, which is showing the sunflower plot. Then I also have my jitter that is being shown in my PDF file. So the whole thing can directly be copied into a PDF file by doing this kind of a simple exercise. Alright. So that is where I come to an end of this session, where we have talked about different kinds of charts, talking about the plots with 2 variables. We discussed scatter plots at length, different kinds of shapes adding to the charts, different mathematical functions, bringing in different kinds of curves, the lowest curve, the lowest curve, and we also looked at the Gann curve and cubic modeling kind of curve. Then we looked at the box plots, bar charts, and Tukey HSD. So for the different categorical variables, we brought in those kind of charts. Then with single samples also, we looked at the histogram. We looked at the pie chart, right? Index charts. We focused on strip chart. And we also had a look at QQ norm, which is the normality check kind of chart. Then for looking at multiple variables, we had pairs kind of scatter plot matrix. We use scope plot for conditional plots across the various groups. Then we also brought in the interaction plots as well. In the special plots, we have looked at the design plots. We have looked at the sunflower plot and even the jitter kind of plots as well. So we have also finally looked at how do I really save the graphics to my PDF files, etc. So that this entire thing should give you an initial layer of understanding regarding the usage of graphics in R, how simple it is to create different kinds of charts, graphs, which can really help you to improvise your understanding to the next level. Thanks a lot for listening to this session. If you have any further queries, you can get back to me by giving me a call on the number that I have given below, or you can even send in an email at vamsidhar@facegurus.com. Thanks a lot for listening to this session. Thank you very much.